He also did his postdoc here at Mila with Joshua and David Rolnick on machine learning for scientific discovery to tackle the climate crisis. And before that, he worked on neuroscience and AI in his PhD in Germany, in Osnabrück. Just a few house rules. So if you have any questions, just raise your hand, like clarification questions, or online, you can either raise your hand or just type it, and I will see if I can ask it. Otherwise, we have 10 or 15 minutes at the end to discuss more questions. Yeah. So we will just put the mic around. With that, with no further ado, I'll hand it over to Alex to talk about multi-fidelity active learning for scientific discoveries.
Thank you, Benno. Thank you for the introduction, and thanks everyone for coming. It's an honor to be here. I'm very happy to be back at Mila and be speaking today at this TED Talk. I'm a backup of someone, I think, but it's still an honor. I have to do this a bit in a rush, but I hope you will enjoy this. I think it's a topic that is more or less transversal to a lot of machine learning and also with some applications. That's why I chose it. I feel like Benno said, feel free to interrupt me with questions. That would be great. I wonder if I can make this full screen, but I guess I can go. So I would like to start with some words about why I work on this specific topic. It's important for me to explain like where the motivation is coming from. And one big motivation is the climate crisis. I usually say that, at Mila and other places, there's no need to explain this, but with the current ongoing, politics, let's say, I think it's especially important to be reminded of this. So this graph is, or this color plot is showing the evolution of the differences in temperature with respect to pre-industrial levels and some projections from climate models into the future, depending on how much we reduce emissions. You can see here on the right. There's time to act, right? This has been a repeated conclusion from the experts that, the time is right now, and the time for action is right now. And I think from science, from the scientific community, we can play our role. Unfortunately, this is an effort that requires, the involvement of a lot of people, a lot of sectors, etc. But I think as scientists, we can play a role, and especially from machine learning, we can do a little bit too. So that's a bit my motivation, or one of my motivations for this. And when we talk about climate change, actually, we care about multiple things. But one important aspect is that it actually has an impact on our health. So a warming planet has a strong impact on a lot of aspects of health. So I won't go into all the details of this. This is a figure from the World Health Organization showing how it impacts from respiratory illnesses to food security to vector-borne diseases, etc., etc. So there's really a lot of aspects from health that affect us directly that are aggravated from a warming planet. Actually, last year, WHO and the World Meteorological Organization said that climate change is the single biggest health threat facing humanity. So seems like kind of important, right? So then why scientific discoveries, right? So let me say a few words about why scientific discoveries can add something to this, to address this challenge. For example, in the latest IPCC assessment reports, it was written that there is a need for improved energy efficiency and the use of alternative fuels, such as hydrogen, for example. We have to improve also energy and materials efficiency, get much better at circular material flows, and so on and so forth. And all this can be tackled in part by new scientific discoveries. So in particular, in the material sector. So there's a lot of areas where new materials could actually contribute to addressing the climate crisis. And then on the health side, I mean, there's a lot we could talk about this, but in particular, I've become quite interested in the problem of bacterial antimicrobial resistance, something that the WHO has focused a lot and raised a lot of alerts. This is not recent. This has been a thing from many years ago. But for example, when it comes to antibiotics, a recent review identified 27 antibiotics in clinical development, and they said that only 6 were classified as innovative, that the approved antibacterial agents are insufficient to tackle this big challenge. So actually, there's a strong lack of new discoveries in this field for antibiotics for multiple reasons that I don't have time to get into. But this is also an area where new discoveries could actually play an important role by helping discover new antibiotics. They wrote that there's no time to wait. So I'm going to be talking about this a little bit too. So all in all, the research I have been doing in the past few years and that I plan to continue during the following years as a professor could be grouped under this umbrella of machine learning for science, where there's work for materials discovery, drug discovery, or other climate-related applications, and trying to find a way to use machine learning for the benefit of society, in particular to address climate change, health challenges, etc. But I think something that's quite interesting and it's exciting to me as a machine learning scientist is that there's actually a lot of feedback as well from the applications, from using machine learning for specific applications like the ones I've just mentioned. There's a lot we can learn from the application fields, and a lot of innovation and research that can be inspired by that. So there is this feedback loop that I quite like, because there's new machine learning research that emerges from the needs of the applications, and that's really what I will talk about today. So if we talk about machine learning for scientific discoveries, maybe it's worth describing first what's the traditional scientific discovery cycle. This is, of course, a simplification, but more or less traditionally it works a little bit like this. There's a scientist or a group of scientists. Obviously, this is a model, right? They come up with ideas. They have some way of testing these ideas, these hypotheses, maybe running some lab experiments, doing some computer simulations. It really depends on the application. This gives us data or insights, can change a lot. And then scientists will refine the ideas and repeat. This has worked pretty well for a long time, but in a context of urgency about certain topics, about certain problems and challenges, it's important to figure out ways of making this a bit faster. So if we want to use machine learning, there's data here. So there's data. Chances are we can do some machine learning with it. So an obvious way is to use this data to train some machine learning model. This machine learning model, we can use it to get some predictions maybe from about our hypotheses or queries, ideas, much faster than these expensive simulations or lab experiments or who knows, and get some data faster. But of course, that is bound to be inaccurate as well. So can we do actually better than this? Especially in problems where the amount of hypotheses, candidate materials, candidate drugs, candidate objects that we can possibly conceive is very large. So yeah, probably we can do better by complementing the generation of hypotheses of the scientists with another machine learning model that's represented here by this little robot, right? So this is the role that a generative machine learning model can play by learning structure from the available data and generalizing that to make predictions or finding candidates in unexplored regions of the search space, and eventually build better queries here to send to either the oracles or the machine learning models. And this is a loop that repeats. So this can kind of be classified or discussed under the umbrella term of active learning, with some generative models in the loop. Yeah, and the idea that I'm going to be discussing here, or the proposal is, well, this can actually explore the candidate space of certain problems much more efficiently. So this is a bit as an introduction to the topic. But before I get into the details of the algorithm that I will present, I would like to discuss some of the challenges that come up in some of the problems. And for that, I have this kind of toy example that I will go through very quickly. So imagine that I give you this problem, very simple, very trivial, which is, okay, you have this Tetris board, very small, and this bunch of pieces, and you have to put them in the boards such that you minimize the empty space. So, and you have to give me one solution. And very quickly, you would tell me, okay, for example, put 3 yellow squares, I fill the entire thing, and that's it. We can give a score to this, which is the number of cells filled by pieces. It would be 12 here. Yeah, very easy, very trivial. We can make this slightly less trivial, but still very easy, which is, how about you give me all the solutions? And this, you will need to think a little bit longer, right? So it's not hard. A few seconds would do, but it becomes a little harder, right? The solution would be these 5 arrangements of the pieces. All of them maximize the score. So far, pretty easy. We don't need a very sophisticated machine learning for this. But how about this? How about I make the board much larger, and I give you the possibility to introduce a lot more pieces. So now, can we find all the arrangements of Tetris pieces on the board that minimize the empty space, or many? Of course, because this is still very intuitive, we know what we have to do. We know what is the objective function very clearly. We can very quickly come up with a bunch of them, right? But actually finding all would be a very, very hard problem. This, you need not a few seconds, you need probably a lot of time. And I don't know if you would manage to do it without using a lot of compute, right? And things get even harder when the objective function that we want to optimize is unknown, in the sense that we don't have a closed form that we can really define and let us say, okay, this is the board or the arrangements of pieces that maximize it. So this happens very often in scientific discoveries, that what we have is perhaps, we can run an experiment, and this costs a lot of money or a lot of time, and then we get a result, but we cannot tell a priori what the result would be. So imagine, for example, that I tell you that these 5 arrangements of pieces optimize the objective function. We would be like, okay, why? So we have no idea. All we can do is evaluate the objective function and get an answer back, and refine and repeat and so on, right? So this is kind of what happens in a lot of problems, right? And to that, let me give you a few examples. Imagine the problem of biological sequence design, where we want to design proteins or peptides, DNA, the candidate space can be very, very large. For example, if we have proteins of 100 length 100 only, it would be like 10 to the 134 possible proteins, right? So that's very large, and this would be examples for DNA. So I won't get into details here, but this is just to illustrate that actually this resembles a little bit this Tetris problem. It could be even easier than the Tetris problem I've just discussed. We could talk about molecular generation. People have proposed or estimated that there is about 10 to the 60 drug-like molecules. That's a lot. Not something we can explore by brute force. And yeah, again, they could be represented as parts, as different fragments that are joined. So it kind of resembles the idea of the Tetris, and that's why I used it. And finally, for crystal structure generation, this is a figure. It's a lot of information here. I apologize. From a paper representing the crystal G-flow nets. But yeah, crystal structures could also be represented as a bunch of subparts, like the space group, the symmetry group of the crystal, and what's the chemical composition, what are the lattice parameters, or where the atoms sit in the crystal, and so on. So you see that more or less this problem of scientific discovery with this, this is to illustrate the challenges that we are facing, and I use the Tetris as a, just as an illustration, but actually it resembles what we face in real world problems. So to summarize these challenges, we are dealing with very large and high dimensional search spaces. So that presents a need for methods that can efficiently search and generalize this underlying structure. Another challenge is that usually the objective function is underspecified. We don't know everything about it. It doesn't capture all the requirements that we want for the problem at hand. This makes a need or presents a need for discovering diverse candidates to deal with this under specification of the objective function. And if we look at existing methods like reinforcement learning, it's very good at optimization, but generally it tends to lack diversity. So of course we can, there's ways to improve diversity. Of course, there is Markov chain Monte Carlo methods that can sample from a distribution. Okay, that would give us the diversity, but they tend to struggle at mode mixing when there's high dimensions. So if we link this problem with this one, then MCMC is not ideal. So actually, we need to combine these different needs and challenges to come up with methods that can tackle them all at the same time. And that's why we have, or actually many people here at Mila have been using generative flow networks, deep flow nets, and active learning as well to address all these challenges. And I will make a little pause here to check if there's questions so far in the room or online. No. Okay. Then, how about we talk a little bit about what are methods in the literature that have been designed for this. So many people might be familiar with Bayesian optimization. It's used a lot in engineering. And essentially, if we take the definition from Wikipedia, Bayesian optimization is a sequential design strategy for global optimization of black box functions. So it's actually for this problem where we don't know what the function is, and it's very useful in a lot of problems because it does not assume any functional forms, for a derivation and so on. So essentially, you have an objective function f, and you want to find the x that maximizes it, like here in this simple one-dimensional case. This covers a lot of what we need, but the problem here, what it lacks, is this idea of diversity. It's an algorithm or a framework for global optimization. It's very good at finding the optimum of the objective function, and there's a lot of literature for it. But if we want to discover multiple modes that are diverse, far from each other, it struggles, and it also struggles sometimes with high dimensions, with structured, so discrete and continuous spaces. So that's why it's not directly applicable for the problems we are dealing with. There is something called active search. I suppose not many people are familiar with this. Active search is something related to Bayesian optimization, but here the idea, usually called Bayesian active search. Here, the idea is that we have a search space as well, and there's two classes, like a good one and a bad one. So imagine the good one is just the white regions here, and the goal is to find candidates, as many as possible from the good class. So it has been used for drug discovery, for materials discovery, but if you think about it, it simplifies the problem. No, it reduces the objective function to a binary class, like the good members and the bad members. And ideally, we want to use and be able to be able to use the complexity of the objective function, because we said that actually it's underspecified. So if we make even more assumptions and reductions, it's gonna compromise important aspects of it. Then there's another algorithm that I expect people to be less familiar. If there is someone who has used this quality diversity algorithm, please talk to me, because this is something I discovered by chance not long ago, and I haven't had the time to explore in detail. Actually, this is very close. It tackles pretty much the same objectives that I have presented, in that it tries to balance quality, so meaning high scores of the objective function, and diversity. And typically this is like a subfield that uses evolutionary algorithms and tries to do this search in a latent space. So yeah, it's actually quite similar, and I discovered it like late enough. It's something that I would like to explore in the future, in the near future. But this would be something to try for the kinds of problems that we tackle. Yeah, and then finally, there is active learning. I would say that this is a very, very large class of algorithms. They can differ a lot between each other, but if we take this figure from a survey by Settles from 2009, he describes 3 classes of algorithms. Let me just focus on these 2: query synthesis and pool-based. The point I want to make here is that the vast majority of active learning algorithms that you find in machine learning conferences, so you go to ICML or iClear and try to say active learning, what you're going to find is methods that use like ImageNet and CIFAR10 and stuff like that, like data sets. So that falls under pool-based active learning, where you have a data set that is finite, that is, you can enumerate it. It's not insanely large, like the kind of problems we're talking about. And with these kind of problems, the methods you use are very different. What we are doing, or what we aim to do, is query synthesis, which is, there's a very large search space. It's potentially infinite, as if you have continuous variables. And the idea is to generate or sample good candidates in that space. And the literature on this is much, much, much smaller, which is why we developed the algorithm that I'm about to present, which is multi-fidelity active learning using GFLONets. And this was published recently, last year, at TMLR. And it's joint work with a student, Nikita, who did amazing work, and Moksh, which you might know, Chen Hao, which you might know too, and Joshua Benjo, which you do know. And yeah, so yeah, before I get into the details of the algorithm, well, actually, is there any questions? Should I go on? Okay. So I'll try to convince you about why multi-fidelity. Hopefully by now it's clear why we want to do active learning, this idea of getting candidates, retrain, repeat, and so on. But why actually multi-fidelity? So let's get back to this toy Tetris example. Imagine I tell you that the oracle, so the thing that will give us the ground truth, or the best ground truth we can get, which is, I said, it's not the ground truth, it's just the best we can have, right? Because it's under-specified. But it actually costs us like $1,000 to evaluate it. Okay, this is not a crazy amount. If you want to do an experiment in the lab or some sort of analysis, it can cost a lot more. I'm thinking, I don't know, an fMRI scan, it costs about that, or it used to be that. Probably it's cheaper now. So this is not crazy for the sake of the argument. So this limits a lot our capability to query and evaluate candidates, right? So that's why need to come up with alternatives. And it's actually the case. It's often the case that in scientific problems, we don't just have one source of information or one source of annotation for knowing how good a candidate is. Typically, there's a lot of things we can do in And yeah, in drug discovery, maybe you can do molecular dynamics. You can have other cheaper approximations. You can have much more expensive but much more accurate simulations, wet lab experiments, etc., etc. So typically, there's a lot of different things we can do, and they come at different costs and of course at different fidelity. So that's the idea, is how to actually leverage the availability of these multiple sources. So, for example, we could have a case where the best oracle is $1,000. Then we have another one which is 100, and one that is noisy but still informative at just $1, for example. And of course, I'm using money here, but think of time, think of whatever metric you want to use to define a cost as an abstract notion. What? Question? Yeah, you can ask now if you want, but you can drink
The
water.
slide answered the question, but I was wondering if those three things are measuring something different with different level of accuracy, or they are actually measuring different things, or do we don't know whether they're measuring different things?
I think typically it's the last case where they measure different things that are somehow related.
Okay.
How they are related, usually we don't really know, or we know partially. Of course, it's not like completely blind. But it's not that this problem would be much easier if we could say, oh, Oracle 2 is like Oracle 1 with Gaussian noise. It's not that, unfortunately. So it's more like whatever. It can be whatever, and that's why we have to develop algorithms that can deal with these kind of challenges. Other questions? No. Yeah, this is an example of what I was saying. So imagine we could synthesize a material and do some characterization. That would be expensive, but we can also do simulations, and maybe we have a machine learning model that has been there, a foundation model that's much cheaper than simulations. Ideally, it's not always the case, actually. So yeah, how can we use the availability of these different oracles? So we developed this active learning algorithm with multiple oracles. I want to remind again this twofold objective, which is we want candidates with high scores of whatever objective function we are optimizing, and the candidates need to be diverse. We want not just one, the best according to our algorithm, but multiple that are diverse. Yeah, for this idea that under specification as well. Yeah, Aaron.
How do you measure diversity?
This is very much so the question for people online, it's how do you measure diversity? And this is a very good question. This is, unfortunately, it's application dependent, and this is one of the things that is a pain to systematically do for a paper, for experiments to actually know. It's really application dependent. So of course, if we are optimizing or searching in a Euclidean space, well, fine, we have a lot of, even there we have a lot of options, right? But if we are talking about DNA sequences or proteins or crystal structures, yeah, who knows? I would like to know how to measure diversity between crystal structures. But I don't think we have an expert here, Michelle, and I don't think you would be able to tell us like, it depends on the application, I guess. Right, we did some experimental evaluation using DNA sequences, antimicrobial peptides, small molecules represented with smiles, and some classical multi-fidelity toy functions from Bayesian optimization literature, just for completeness. Yeah, and I think, we can never be sure of this, but to our knowledge, it's the first multi-fidelity active learning method for biological sequences and molecules, so applied for this kind of problems. There's, of course, multi-fidelity Bayesian optimization methods, multi-fidelity active learning, but actually used for this kind of complex problems where there's structured data, very large spaces, high dimension, etc. We were not aware of anything before. So I'll get into the algorithm now, finally. Again, we have an oracle, and I'm starting by single fidelity first for clarity. Imagine we have an oracle. We're going to call it F M, and lambda here is the cost, okay? The cost of this oracle. And then we can have a set of data, x's here, xi. We have b of them. We annotate them, evaluate the oracle, evaluate the x's with our oracle. And this gives us a data set where we have x and f of x. Cool. We can use this data to train a machine learning model. We're going to call that a surrogate model, taking the terminology from the Bayesian optimization literature. And the surrogate model is a probabilistic model, which models the posterior of the oracle given the x and the data, the data set that we have at this time in the loop. And if we were to do Bayesian optimization, let me take a step back. If we were to do Bayesian optimization, we would select an acquisition function, which measures the value or the worth of annotating candidate X. And what Bayesian optimization does is trying to optimize this acquisition function to select the best of that, the optimum of the acquisition function, and feed it back to the oracle and repeat. With GFlow-nets, we do something a little bit different, which is we are going to have a GFlow-net that is able to sample candidates, X's, okay? Object X. And what we do is to, instead of optimizing the acquisition function, sample from it. We use the acquisition function as a reward of the GFlow-net. And for those who are not familiar with GFlow-nets, essentially, they are designed to do sampling instead of optimization. So the idea is that in other words, instead of sorry, I'll take a step back. We don't want to just optimize. We want to sample from the acquisition function, and the idea, the objective is to have diversity, right? If we sample from the acquisition function, we might get diverse objects that have good values of the acquisition function. That's important, and I made it very messy, so I want to make sure that people got this idea. Should I rephrase? Okay, so we are sampling from the acquisition function instead of optimization. Apologies for that. I made a mess. Yeah, that's it. So after training the GFlow-net, we can sample from it, and it will give us objects, X's, that are supposed to have good values of the acquisition function, so that are worth annotating. We can select maybe B according to our budget, and yeah, send them to Oracle, get more data, retrain a GFlow-net, and repeat. We can do it multiple times until we exhaust our budget, and that will be it. Now, how do we make this multi-fidelity? Well, now instead of just one oracle, we have multiple oracles. They are going to have different costs. And yeah, we assume the lower the index, the lower the cost, just without loss of generality, right? And now, instead of sending all the X's to the same oracle, we have the freedom to say, for this X, this M, this oracle; for this other X, this other M. You know, so we can decide which oracle to use for each data point. And this makes a multi-fidelity, let's call it multi-fidelity data set, where we store the X, f of X of the oracle that was used, and also the index of the oracle. So that's everything. And now we want to train our surrogate model, but the surrogate model has to be multi-fidelity to accommodate the multi-fidelity aspect of the data. So now it's the same as before, but now it's the posterior of oracle M, given X, M, the index of the oracle, and the dataset. And something we propose in the paper is to have GFlow-net sample both X and the oracle. So GFlow-net is supposed to sample from the reward function, so we make it sample both which oracle should go with this X. So kind of bound the two. Question?
Yeah, sorry, very basic question.
Sorry, this is very basic. I'm a little confused. What is the difference between an acquisition function and the oracle function? Like, what is
difference between acquisition and oracle?
Yeah.
Yeah, the oracle is the objective function. That's what we want to have high scores of this objective function. The acquisition function it's a function that tries to capture the worth of annotating a new X. And there are many different acquisition functions that have been proposed in the Bayesian optimization literature. And maybe the idea, if you're not familiar with that, you can think of it as ways of balancing like exploitation, exploration, and they take into account the uncertainty. So this is a probabilistic model. So that's the acquisition function uses the probabilistic aspect of the surrogate model to model the uncertainty. So for example, you could design an acquisition function that gives high values to regions of the search space of which you have no data at all, right? Because you don't know what's up there. So if you give high value to unexplored regions through your acquisition function, that would give high values of the acquisition function, even if the oracle is low there. But again, there's different acquisition functions, and it's a design choice. There's another question.
Thanks. So here you have multiple costs. I'm not sure I understand why you have multiple costs, and then why in the next step you said you sample the X with the cost instead of, like, my intuition was that why not combining them? Do they not coexist? So I'm not sure I understand that part.
Yeah, it's a good question. I haven't got there. The why we have a cost. So the cost actually goes in the acquisition function. So here GFRNet samples X and M and uses as reward an acquisition function that depends on the oracle as well, the M. And the way, or one of the ways it depends on the oracle is by including the cost. So you're going to see in a few slides that the cost is essentially the denominator of the acquisition function. So the higher the cost, the lower is going to be the value of the acquisition function. Yep. Yeah, how is alpha informed by the posterior? In a complicated way, I have a slide with those details. We use an acquisition function that's called max entropy search. I'm going to show, but you know the multi-fidelity surrogate will have some Gaussian processes, and then you use some kernels to, you know, I'll show it in a slide. But yeah, unfortunately it's not a short answer. And again, that's a design choice. It's one of the things that you could just replace. We use one, and it's something we haven't explored, but things could work better by choosing different acquisition functions. Okay, any other questions about the algorithm? Michel?
Can you repeat my question?
Okay.
So for each data, you only have like one oracle, the answer of one oracle. So you cannot have multiple oracles.
Yeah. The question is, can we use multiple oracles for a single data point? Technically, yes. It's not something we have explored. So I will give this answer to a lot of questions potentially, because this was pretty new. And there's so many components here that we had to figure out. So there's a lot of different things that could be done differently, that could be improved, and that we haven't really done. And this is one. If it's useful for something, it would be great to incorporate it and but it wouldn't, it's not immediately obvious to me how to do that, but it's yeah, should be possible. Yeah, that would fall. Yeah, maybe what you're talking about as well is like multi-objective, multi-fidelity, which is something like multi-objective, so multiple properties of a material, for example. That's something that would be really cool to do. We haven't done it. It's like another layer of complexity here, but why not? Future work. All right, running out of time, so I'll get to show you. You know, I can tell you, okay, this works pretty well, but I think my duty now is to try to convince you with some results. So I'll try that. So we compared with a bunch of baselines. One is single fidelity version of what I have just shown. So the first thing I presented before adding the multiple oracles. And another baseline is sampling random candidates instead of using GFlonet, and then you still rank them with the acquisition function, which makes this specific baseline a pretty strong baseline. In the literature of baseline optimization, sampling randomly and then using the acquisition function is typically a strong baseline. Then there is another baseline, which is exactly the same algorithm. So this, but we don't let GFlonet sample the index of the oracle. This was essentially to test what is the added value of this design choice. Finally, again, the same algorithm, but replacing GFlonet with a reinforcement learning algorithm like PPO, because yeah, it's possible, and that was to test what's the value of using GFlonet and having this idea of sampling from the acquisition function instead of optimizing it. Okay, let me show you these results, which tackled the problem of generating or discovering small molecules represented as sequences of selfies. There's 26 tokens, but it's just a sequence, right? You add one token at a time, up to a length of 64 in our case. And this was to generate sequences with good adiabatic electron affinity, which is relevant for organic semiconductors, photoredox catalysis, and organometallic synthesis. This was some work done by Chen Hao. He works on this in this problem. And then this was interesting because here we did a bunch of more or less toy experiments, but this one was one in which, it's actually a problem in which one of the co-authors is working, and the oracles that we used here, 3 oracles, had costs that reflect the actual computational demands of the oracles. So that was a nice experiment to try. Okay, so the results I'm going to show you are as follows. On the x-axis, I have the fraction of the budget, the amount of budget that is used at a point during this loop of active learning, right? And in the y-axis is the objective function. In this case, it's an energy. The higher, the better. And what we are showing here is the mean, the average of the best 100 candidates that have been found at a given point during the loops. Okay. So if I start with the single fidelity active learning method using GFlonet, we see something like this. At the beginning, of course, the mean is low, and as we do more exploration and use more budget, it increases. Okay, cool. This was published or done in a previous paper. Here in pink, we have the random baseline. So it's slightly worse than the single fidelity method. In some cases, it's a little bit better. Like, again, this random baseline is kind of strong sometimes. And here in orange is already the multi-fidelity. So this is already multi-fidelity with GFlonet, but here we are randomizing the oracle chosen. Okay, and finally in blue, it's the actual complete method of multi-fidelity GFlonet, where it samples as well the oracle, and we see that it improves substantially over the other baselines. And I mentioned reinforcement learning, so let me add it to the plot in kind of brownish color. Here is the reinforcement learning algorithm. So essentially, it's all the same, but instead of GFlonet, PPO. And we see that at the beginning, it's faster at finding good candidates. It's very much expected. It optimizes the acquisition function. The acquisition function is going to place high value to points with high scores. So it's normal that it actually, it's actually expected that it's pretty good. But here, what's missing is one ingredient. I talked about 2 objectives: high scores and diversity. So we are not seeing the diversity here, but we can add it to the plot by these dots, and these dots essentially measure or indicate the diversity of the 100 samples that we compute on which we compute the mean, right? So the darker blue the more diversity, the more yellow, the less diversity. So we see that the GFlonet-based methods, as well as the random one, have very high diversity, while the reinforcement learning method, it very quickly finds good candidates, but they are not very diverse. So again, this is expected. We had observed this in a previous paper doing single fidelity active learning. So this is kind of what we were expecting. And then eventually reinforcement learning, as you keep adding candidates, it ends up having diversity, but you see the way it achieves high scores is by sacrificing diversity, while the GFlonet, we observe consistently that it keeps good scores on high diversity. That's kind of like the main result. And like I said before, we did this with multiple different experiments, DNA, proteins, small molecules, and the results are quite consistent. So this is with small molecules. Yeah, it's very similar. Yeah, I won't spend much time because I'm running out of time, but very similar results. This is with DNA. Again, here in blue is the multi-fidelity GFlonet. In some cases, we have not here. Yeah. Anyway, let's keep that. But yeah, very consistent results. Yeah. Question? The first plot, yes. I cannot hear. Sure.
So I'm wondering if the density of the dots also says something, because the first dot on the reinforcement learning algorithm seems to have the same color as the other.
This one here?
The first one, yeah. The
This one here?
the lowest cost on the reinforcement learning, I think a bit upper.
Like here and there?
Yeah, that one, yeah.
Yeah. This is more diverse than this one, for example.
Yeah.
So at the beginning, it might find it's the first round. So it finds this. Of course, I'm making a hypothesis of what's going on. It finds a bunch of candidates that are relatively good, not as good as they can be, later, but they are relatively good and they are diverse. But then it finds potentially many good candidates or high scores that are perhaps in a small region, and that's why the diversity gets compromised here.
So you have dots, because I wasn't seeing any point in between. Okay, they are just light colored. Okay, I see. Okay.
Yeah, I mean, these dots, it's always the diversity, according to this color map, of the 100 best candidates. Yeah.
One more question.
It's coming back to the question of earlier. Like in that case, there is a metric for diversity.
Yeah,
Do you
in
know
this
how
case,
to
it's
define it. Yeah.
in this case it's a metric of diversity that compares sequences. What was this? Because it's different actually for the DNA, for the proteins. I don't want to say something wrong, but there is in this case there was a metric of diversity that Chen Hao and the community uses for that problem, and we used that one. I don't venture a wrong answer because I don't remember it right now. But yeah, it's a domain inspired metric of diversity. Yeah. For DNA, for example, it was like counting how many nucleotides are different.
Did you measure whether the acquisition function was correlated with the diversity metric that you
No.
use? Because I'm wondering why, like, the PPO baseline finds this kind of subspace where it's not very diverse and then kind of goes to a more diverse space.
Well, every round, as you acquire more data, the acquisition function is going to change. So it potentially will, most likely it will assign high values of the acquisition function to different regions.
Mm-hmm.
So as you keep adding data, so if, for example, if this is our optimization space, and now we're at round 1, and here we have high values, maybe here too, and the reinforcement learning will focus on this one because it optimizes, it gets data points there. We add this data to the data set, Oracle, add to the data set, retrain. The next time, the acquisition function will not have high values here because, yeah, we already, it's not uncertain anymore. So maybe now we have high values here, and
Okay.
it gets data there, and so on and so forth.
So
So
there's
it's
some
also normal
notion of
that the more
uncertainty,
you try, you're supposed to keep exploring. So yeah, if you run this until infinity, you will have diversity for sure with any method. The idea is to have it like efficiently and as early as possible.
There's one more question online from Philip. I think you can just speak.
Yeah.
Hello. Thank you. Yeah, I do have a question. If you go back, maybe it's more visible on the previous slide.
This one?
Yeah, on this one, it seems that the RL approach finds some candidates that are better. Do you think there is a way to incorporate these findings from RL to terminal states from the GFlowNet approach to enhance the GFlowNet?
Yes, absolutely. Yes. So we did very, very little in, for example, like local optimization for the candidates because before passing them to the Oracle. So this was enough engineering work to do just like this. But there's so many aspects that can be improved. The one you mentioned is one. So actually improving, doing some local optimization for the candidates that are found, that would, yeah, it's bound to improve significantly the rate at which good candidates are found, especially when it comes to scores.
So using different method and combining them achieve even better results.
Yeah.
Okay. Thank you.
Yeah, so I'm running out of time, unfortunately. So yeah, this is, for example, peptides. You see here the budget is in log scale. So this was one example where we found the multi-fidelity GFlowNet to be quite good. But yeah, in general, we saw more or less consistent results in that GFlowNet, multi-fidelity active learning, with this GFlowNet as a sampler, finds high scores and diversity quite efficiently. Yeah, I will just skip to the end. You can check the slides. This is more the details of the surrogate models and the kernels that are used. And here is the details of the acquisition function for reference. Unfortunately, I don't have time, but I'll leave it there. Yeah, there's some details of how the GFlowNet was built. And I would just mention here some ongoing or planned or potential applications. So for example, discovering materials with high ionic conductivity for solid state electrolyte batteries. This is a problem where there's very, very little data. So we have just put together some data taken from the literature, and the data set is probably the largest so far, and it's 600 data points, okay? So this talking to machine learning people sounds ridiculous. I hear some laughs. But yeah, that's the thing. Like here, it's an application where actually using multi-fidelity active learning could be quite impactful. Same for discovering novel antibiotics. Imagine this lab-in-the-loop approach. So that's something we are also working on. Designing electrocatalysts for sustainability processes. Again, here it's something where we have access to multiple sources of information, of ways to characterize electrocatalysts, and that can benefit from that too. And yeah, I'm sure there's a lot more applications, and happy to chat if you have ideas. And yeah, this is a summary slide highlighting again how the current machine learning methods don't fully address the needs that we had for some of these applications, and how there is a need for developing methods that can efficiently discover diverse candidates in these challenging, combinatorially large, high-dimensional search spaces. And yeah, we have proposed this multi-fidelity active learning methods. The code is available online. And yeah, I want to finish by acknowledging the work of my co-authors, Nikita, who was a student. She was a bachelor student, actually. She did amazing work during her internship. Of course, Mox, Chen Hao, and Joshua as well. So thanks to them. Yeah, the slides are here in case you want to check that. The paper is published as well. And yeah, we're actually looking for students, collaborators to work on this kind of problem. There's so much that can be done. So get in touch if you're interested. And thank you very much.
Thanks, Alex, for the fascinating talk. Now we have some time for broader questions, either online or here in person. Just raise your hand and I can come with the mic.
Yeah, thanks for the great talk, first of all. I have one question about the framework in general. So we're sort of doing this multi-fidelity thing, but to develop more oracles, we need an oracle in the first place, right? We need a high fidelity oracle.
Right.
And so is there sort of an analysis of like a cost performance analysis for developing new oracles with different fidelities and how much that would cost and what the performance increase because of introducing these new oracles is?
Developing new oracles, that's relevant and important in some applications. In other applications, the oracles are already there, and that's what actually inspires this kind of method. So if you go to like physics or molecular modeling and so on, there is already a lot of methods that scientists use that they use in different contexts depending on how much you're willing to spend in terms of time, resources, etc. for a particular application. So that's already there in a lot of applications, and there's no need to develop new ones. It's more about how to actually select efficiently which ones we use. Often we need to have like very cheap oracles that are as good as possible. That's kind of the role of machine learning as well. Typically in many of these experiments, the cheapest oracle is a large machine learning model that's good enough to tell us something about the problem, but it's going to be inaccurate, of course. And that's where work can be done. I don't know if that answers your question.
Yeah, thanks.
Michelle?
So thank you for the very interesting talks and ways to come up with new materials or different discovery. I would like to understand how does this multi-referencing or multi-fidelity works in particular, it's like when you have some oracle which has lots of error in it, but seems to have find like a good region or space, do you then decide, but does the algorithm decide like, okay, I'm going to get more accurate data in order to get more precise like values, or is it like it's more complicated than that? Because you didn't mention that you have these different oracle, but you don't qualify the uncertainty of these.
Let me go back to the slide showing the algorithm. So you're talking about the inaccuracy of the oracles. So about the best oracle, here we assume that that's because it's typically the best we can get. We assume it's just good, and there's ways of relaxing that assumption, but things get complicated. Not that this is not interesting to explore, but this is kind of an assumption here. The other oracles, you pretty much assume that they are wrong, they are inaccurate, but they are still informative. But we have nothing in the algorithm that incorporates the information about in which ways they are wrong. That's not something we have explored. Again, I think it's very interesting, but we simply all the assumption here is that okay, they are inaccurate, but still informative, and that's how the algorithm is built. The uncertainty is incorporated in the surrogate model. So the surrogate models, the uncertainty you have by the set of all your oracles about the search space. That and of course, this modeling of uncertainty is actually very challenging. So it's also bound to be wrong. So it's okay, but we have to live with that. But yeah, that incorporates the uncertainty you have about the search space, given the oracles, given the data and which oracles have been used to annotate which data points. So yeah, it's kind of a vague answer, but yeah, maybe to your question specifically is like, no, we don't have a way yet to introduce how exactly they are wrong, the oracles.
Okay, there's one more. Yeah, hi, thanks for the talk. Another maybe question about the acquisition function, sorry. I'm just trying to understand it better. Like, suppose the oracles we were certain about all the oracles, like they were like.
Suppose what, sorry?
We were certain about, like they were good oracles. None of them were noisy. Like they gave good answers and they were low cost. Would we need an acquisition function?
If all oracles are, so they are all the same?
Well, they give you signals about different things. I don't know.
I don't understand. If they're all the same, is like just having one oracle?
They're not. The oracles are different. Like they give you, I don't know, information about different things, like how good protein is at doing something or something else. Like I'm just trying to understand the exact role. So the acquisition function is really about the uncertainty, like the inherent uncertainty of the oracles, right?
The acquisition function actually measures the one we use. Again, there are multiple choices. We use one that is called maximum entropy search, and it's this expression. It's the mutual information between oracle M, so lower fidelity than the best one, the mutual information between that and the optimum of the best oracle.
I see.
Okay, so the maximum value of the best oracle. This is it uses the maximum value because this is coming from the Bayesian optimization literature, which is focused on optimization, and then the mutual information between these two is divided by the cost of oracle M. Okay. So that's exactly what it does.
Okay.
I would expect that, or I would say, like one avenue for improving this algorithm is coming up with acquisition functions that are actually better suited for this problem of diversity than just optimization, because this is really tackling optimization.
Right.
But again,
yeah,
there's really a lot of acquisition functions and room for improvement here.
Great, thank you.
We chose this one because there is an efficient implementation of it, and it's pretty recent. You see, 2021 is not like 10 years. Yeah, it works. We took it. Okay, there is evidence that it works well, so let's use it. But that's really it.
Okay, there's one more question online from Philippe. Once trained, do you observe that GFlow-Nets avoids the weak surrogates? In other terms, is there diversity in the surrogates that are proposed by the GFlow-Net?
Can you repeat, Benno? Sorry.
Yeah, you can also, if you wanna, in the chat, you can also read it again if you wanna. Once trained, do you observe that GFlow-Nets avoids the weak surrogates, quote unquote?
Once trained, if GFlow-Net avoids the weak surrogates, I would say that it avoids the low score regions. I have one slide that before. This is just in 2 dimensions with a function that's called the Browning function from the Bayesian optimization literature. And this aims to show a little bit what happens in this toy 2 dimension, which, just for illustration purposes, this is not the kind of problem that inspires our algorithm, because this is too simple. You don't need a GFlow-Net here, you don't need active learning. So just take it with a pinch of salt. But what we see here is the following. So the stars are the modes of the maximum value, the areas of best values of the function that we're optimizing. And we start with training data where the crosses are. We deliberately put them away from the modes at the beginning to make it a little bit more challenging. And at the beginning, well, at the beginning, these are, it's not at the beginning, these are the points where the GFlonet, or the algorithm, I would say, the samples were using the low-cost oracle, okay, the lowest cost. So they did a little bit of exploration in the bad areas, but they still come closer to the modes. This is with the next oracle, and then in orange we see where the best oracle was used, like closer to the modes in general. This doesn't answer at all the question that was asked, but you know, add some information, because it's not an analysis like what oracles are selected at what time and so on. We haven't done an in-depth analysis of it. And the other question was, is there diversity in the targets that are proposed by the GFlonet?
No, it was just a reformulation of
yeah.
But so it means that the samples that were proposed using the surrogate with cost 1 were pretty bad comparing with the other surrogates. Am I correct? Do I understand correctly?
I mean, the chances are it uses. I mean, the general idea of what we have seen is that the low cost oracles, not surrogates, the low cost oracles are used for exploration, kind of.
Mm-hmm.
Of course, take with a pinch of salt. And then the expensive oracles, or oracle, is used kind of for confirmation. So once the low cost oracle has given you information about, okay, there's good values here, then expensive oracle can confirm.
Okay.
That's kind of what happens, or what seems to happen.
Okay, one last question. Yeah.
It's very, very just fundamental, because I'm seeing all of these different oracles, and I had in mind, you know, you have a certain material and you could measure different things. So you could measure like heat conductivity, electrical conductivity, magnetization. So these are like different quantities, but then these would like correspond to the different FM. How do you then like compare them? Because they're just not the same quantity.
That's not exactly what we do here. It's not that we use oracles that measure different things. It's rather oracles that measure the same thing, but with worse fidelity. So imagine you have I don't know, let's say molecular dynamics simulation that you can, to simplify things, there's multiple things you can do, but you can run it for 1 hour, or you can run it for 10 days. So you're measuring the same thing in principle, but at different costs. And of course, if you run it for 10 days, chances are you're going to get a better estimation of what you are measuring in your particular problem. And so it's more that idea than measuring different things. But what you are saying, measuring different things, not done at all. I think it would be very interesting as well, like how measuring different things could, yeah. But that falls. I would label that as multi-objective active learning.
Okay, thank you.
Which is a thing as well. Multi-fidelity, multi-objective. I'm not aware of any work of that.
Okay, thanks for all the questions and the great talk again. And yeah. And since this question keeps coming up, you can feel free to like message the speaker if you want to see the slides. And the talk will be on YouTube in a few days, or on the Mila T-Talk website. Okay, thank you.
Thank you all.
Thank you.
I'm tired and don't want to talk.